Okay, great. So welcome everyone to this new seminar from the Quantum Computing Association of EPFL. Today we are very lucky to host Stefano Barison, who is a PhD student at EPFL, who very recently joined EPFL in the lab of Professor Giuseppe Calleo, who also arrived very recently. So we're very happy to have this team. So the talk of today will deal with variational quantum algorithms, and specifically for applications in the study of quantum system, the simulation of quantum systems more specifically. I'll tell a few words about Stefano. So he's Italian. He did both his bachelor and master in physics at the University of Milano. And he recently collaborated with IBM for his thesis on the study of nitrogen-copper compounds using hardware-efficient quantum algorithms. And so I figured that this work he's done so far is highly related to what he's done in the past. And so, as I said before, he's a PhD student who is in the Computational Quantum Science Laboratory, supervised by Professor Giuseppe Calleo, who also deals with the study of quantum system of many-body physics problem with classical machine learning techniques. Today, we're going to focus on the use of quantum computing resources for those matters. And I'll let Stefano take the floor right now. Thank you very much, Stefano, for this presentation, and we're looking forward to hear everything. Thank you very much.
Thank you for inviting me. So let me share the screen. And okay, I'm not sure you should see the screen.
Yes, all good. Yep.
Okay. I also should start. Okay, reproducing, but okay. I have the tools of Zoom over the tools of Keynote. Okay, so thank you for inviting me. And as Arthur said, today I will be discussing the simulation of quantum systems on quantum computer, in particular on what we can do today to simulate a quantum system on quantum computer. So on very noisy near-term devices. And for this reason, we will see how to use variational algorithms to do it. Okay, so I will discuss about our work, which we did very recently, like 2 months ago. We published the paper in the preprint. But I will start a little bit discussing about the many-body problem and how we can simulate quantum systems on quantum computer. Then I will introduce our work, we'll discuss the results, and then I will discuss a little bit about some outlooks of this work. So basically, why we want to study many-body systems on a quantum computer. Yeah, this is basically related to the quantum many-body problem. And what is it? Yeah, we know that we can use quantum physics to study basically everything. But let's consider like a simple, very simple system that is a spin 1/2 particle. And we know that its generic state can be written as the following in the following way, as a linear combination with of two basis states that are basically the spin up and spin down that here I have represented in the quantum information formalism with 0 and 1. And this linear combination is a linear combination of two complex values, alpha and beta. So this is very simple. If yeah, I can impose that the sum of this the squared modulus of these two values is equal to 1 to have the state that is normalized. But mainly just by storing these two values, I can reproduce every possible state of this spin 1/2 particle. But if I generalize to a generic n qubit state and spin state, we can see that our problem scales up really fast because the number of coefficient that I need to reproduce generically the state, scales up exponentially with the number of spins. So if you think as x here as the number of the a number in a binary digit, so n binary strings, I can have 2 to the n binary strings. So I want a generic state is represented by a linear combination of these different strings, and all these strings are weighted with some coefficient, complex coefficient that has these alpha x. And as an example, if I have 120 spins, this coefficient will be 2 to the 120. That is more or less like the number of the atoms in the entire Earth. So if I want to store this wave function completely, the most generic wave function, even if I use only one atom to store these complex values, I would need like an entire Earth of atoms to store this wave function, which is yeah, incredibly difficult for our computation. And moreover, we want to know how this coefficient evolve, because we know that if the state is not an eigenstate of the Hamiltonian, this coefficient will vary in time following the Schrödinger equation. So yeah, we want to improve this estimation. We want to find methods to study many body systems, and yeah, we can do it basically also on classical computer. There are many ways to study systems on classical computers, like exact diagonalization methods, which are the most expensive one. We can use quantum Monte Carlo methods, yeah, neural networks, as we do also in the group, to reproduce these quantum many-body states. So there are a lot of ways to classical, that means on classical computers, study quantum many-body physics. But also the quantum computers have been proposed to do this. Why? Well, basically because to know how quantum many-body systems behave, we have to solve the Schrödinger equation. And we know that the formal solution, if the system is closed and the Hamiltonian is not time dependent, can be represented as I represented here, as a time evolution operator that acts on the state at time t equals 0. So we know what are the coefficients at time equals 0, and we apply this time evolution operator, and we have the state at every time t. And if we impose a basis to represent this state, basically this time evolution operator is a matrix, and also the Hamiltonian is a matrix. So we have a complex Hermitian matrix that is exponentiated and then applied to a vector, to a complex vector. So, and this matrix is exponentially increasing in size. So again, the same problem as before. We have an exponential demand of memory and resources for our computation. But it has been demonstrated that the time evolution operator can be efficiently implemented on a quantum computer if H, as that is the Hamiltonian, is a sum of local terms. So sum of terms that acts only locally on a subspace of the Hilbert space, which is more or less what happens quite always in physical Hamiltonians. So we have like two spins, two body interactions. So we have terms of the Hamiltonian that acts only on the subspace of these two particles that interacts, and not all the particles at the same time. So these are local terms. And this has been demonstrated by Lloyd in 1996. So what we can do, we can take the time evolution operator and approximate it using the Trotter-Suzuki approximation. what does the Trotteso-Zucchi approximation? We have our time evolution operator, and we decompose it into a product of local time evolution operator. And this product is repeated n times. And every time we repeat this product, we increase the accuracy of our decomposition, of our approximation. So if I go to infinity, if n goes to infinity, this approximation becomes exact. So this is not an approximation, this is an equivalence. But we are limited. We cannot go with n that equals infinity. So this is always an approximation. It is exact also in the case if the local terms of the Hamiltonian commutes between them. So it's yeah, just to be clear, it's right to say this, but we are mostly interested in the case in which the local terms do not commute between them. So it's always an approximation. And so we have this main scheme about how quantum simulation and quantum computers works. I've taken this picture from a paper of Tacchino and others from IBM. It was maybe now he works at the IBM, and then when he wrote this paper was in University of Pavia, I think. And I think it's pretty nice, so I suggest it to read it if you're interested. So we start from a physical model that we want to study. We have our Hamiltonian, we have our time evolution operator, and we map this system into a Pauli Hamiltonian. So that is the Hamiltonian that acts on the qubits and whose states are states of the qubits. And then we can decompose the time evolution operator into a set of gates that are going to compose a quantum circuit, and then we apply these gates to our qubit states and then measure the states at the end. And by measuring it, we have some information, some observables about the system we are studying. And then maybe we can make a new prediction or study different systems and so on. So yeah, this is a loop that goes that finish when we have all the information that we want about the system. And so this is basically done. This is all we have to do if we want to study quantum system on a quantum computer. But this method has some limitation. In particular, right now, at the moment, because it's not very feasible nowadays. In particular, we know that this approximation, the approximation error decreases arbitrarily if we increase the number of substeps. But also the circuit depth increase when we increase n, because we have these same operators that are repeated n times. And also, yeah, it's a side effect. Also, the circuit depth increases with the system size, and this is pretty bad because we know that our quantum gates now have a very high error rates, and we cannot correct these errors. So the more gates we had, the more the results will be dominated by noise, basically. And to this, we also have to add a readout error, that is an error associated to the fact that we are measuring the qubit, and also the fact that we have a statistical fluctuation, so a statistical error based on the fact that we are measuring the qubits a finite number of times. So we don't have we know that every quantum algorithm is intrinsically statistical, based on the fact that we measure the qubits multiple times to have the coefficient of this, if we want to reproduce the state. We cannot access the whole wave function at once, but we have to do it in a finite number of times, so we have a statistical fluctuation. So we have the Trotter error, the gates error, the readout error, and the statistical fluctuation. So it's a scaling up of errors that basically after a few steps of trotter, we are basically dominated by noise. The state of the art, which was also represented in the keynote paper, was like 5-6 trotter steps on an easing chain of 5 qubits, 3 to 5 qubits. And it was in 2019. So maybe right now is a bit better, but just to give you an idea, it's not 25, it's not 100 of trotter steps, it's 5, 6, 7, something like this. So yeah, we cannot really go so far in time. And for this reason, hybrid quantum algorithms have been proposed. They are hybrid in the sense that they combine a quantum computer with a classical computer to lower the work that a quantum computer has to do and to reduce the impact of error. Basically, all the variational algorithm works in the same way. We have our exact state, that is the time, in our case is the time evolved state, but we have to approximate it, and we approximate it with an unsat state that is parameterized by a certain number of variation parameters. And yeah, basically this ansatz is made in a way that it's easy to decompose in a quantum circuit. So we decompose it on a quantum circuit, and we use these ansatz to measure some observables. And then, with all these quantities measured, we communicate this data to a classical computer that has the role of determining how to update this parameter. So basically, yeah, it's going to determine the shift of this parameter or the variation of this parameter, like a derivative with respect to time, or something like this. And yeah, the way it determines is different from algorithm to algorithm, and is based on the fact that we are looking for the ground state or the time evolved state. They are pretty different algorithms. So this is the main structure, but all the algorithms are different in some way. And in 2017, a group of researchers from Oxford devised an algorithm, a variational algorithm, to study the time evolution of quantum systems, so the dynamics of quantum systems. And these methods is based on the time-dependent variational principle, which is a revised, a slightly modified version of the Mac-Lachlan's variational principle proposed in 1964. And I'm stressing on it because, yeah, the initial variational principle was proposed for classical simulation of quantum systems. So back in a classical simulation of quantum system, we had the same problem. So we had to parameterize our wave function and then find a way to update our parameters to reproduce the property that we want. And so how it works? They basically solve this equation, which is the Euler-Lagrange equation of motion, which is a linear system. And the solution of this equation is a vector, and is a vector of derivatives of parameters. So yeah, we know how to update the parameter. So if we solve this linear system, we have these derivatives, so we can update our parameter with this. We know which is the time step. We know the derivative, so we can do like a first order Taylor expansion and improve modify our parameters. And where does the quantum computer enter? It's basically because these coefficient of the linear system are measured on a quantum computer. So we have the matrix elements and the known elements of the vector VE measured on a quantum computer. So they basically use the quantum computer to measure these elements, and then they solve the linear system on a classical computer, and then communicate the update parameter to again to the quantum computer, and so on. So this method works, of course, but it has some problems. In particular, the fact that we have to measure all these elements is a problem, because we have a matrix, so a matrix that depends upon the parameters. So we have to measure a quantity of circuits that is proportional to n squared. And then if we have to solve this linear system, we have to invert the matrix, basically, in the simplest form. And this is a problem, because analytically this is not a problem, but if we do it numerically, it may be that the matrix Mij can be ill-conditioned, so with very low elements on the diagonal and close to zero element of diagonal elements. So it can be very, very difficult to invert. And moreover, we know that we have the errors due to the fact that we are measuring statistically, and as I was saying before, a lot of errors from a quantum computer. So it's a really unstable procedure. And moreover, this matrix is the imaginary part of what is called the quantum geometric tensor. And the quantum geometric, its imaginary part is skew symmetric. So the diagonal of this matrix is all zero to preserve the skew symmetry. So it's if its off diagonal elements are close to zero, it's unstable by definition. And we cannot improve this inversion. Basically, what we do numerically to improve the inversion is to add a little shift on the diagonal, but we cannot do it because it will ruin the skew symmetry of the matrix. And at the end, last but not least, these are not simple expectation values. We know that on a quantum computer we are very, very good in measuring expectation values, but here we have not an overlap between two different states. So we have to slightly modify our quantum circuit, and yeah, we have to add ancillary qubits, controlled operation. So we basically have to do an Hadamard test. So yeah, we knew all this problem, and we worked on it to propose a better way to study the dynamics of quantum systems. And the solution, I think it's very, very simple. In the idea behind the solution is very, very simple. Instead of solving the equation is the same, basically, we will see it, but we sample the solution, so the parameter shift, and we improve upon this solution iteratively. And we do it by maximizing this overlap, this following overlap. And this following overlap is the overlap between the state at with some parameters, time evolved with a trotter time step, and the state modified by a shift of the parameters. So basically, we are approximating the time evolved state with a shift of the parameters. Okay, so we can maximizing this overlap or equivalently minimizing the cost function that we wrote to make it independent of the time step in the limit that the time step goes to zero. But yeah, you can the picture is that we want to maximize the overlap between the real time evolved state and the approximated time evolved state with the shift of the parameters. And the algorithms has the following structure. So we start with a fixed time step. We propose a parameter shift, and then we measure the gradient of the loss function using what is called the parameter shift rule. That is a way to compute gradients on quantum hardware that does not require additional qubits or controlled operation. It does require only to sample the same circuit by shifting some parameter by a fixed amount So it's yeah, we need to sample 2n circuits for n parameter, but we will see it later. But it does not require extra qubits or whatsoever. Then we update our parameter with a gradient descent algorithm, and we check if our calculation is converged based on some convergence criteria. It can be like the overlap has exceeded a certain threshold. The overlap has to go to 0. So maybe we fix an overlap threshold. And then if it's converged, we update the parameter and we restart this loop again until the end of our simulation. So here we have a figure that it's pretty much the same, but just wanted to show, yeah, like the abstract representation. We propose a variation that is this vector in gray vector, and by iteratively updating upon it, we follow the real evolution. And to compute with the loss function, we use basically here the overlap. We use this circuit that I have picked here. That is CW plus the W. That is the ansatz with the parameter shifted, and the ansatz with the parameter not shifted but inverted, because we are considering the bra instead of the cat. And in the middle, a trotter time step, a single trotter time step. And yeah, that's it for the algorithm. But we wanted to check if this algorithm has some relationship with has some theoretical basis, so relationship with the variational principle. And fortunately, the answer is yes, because if we want to find the parameter shift that maximizes this overlap, so basically we expand to the second order, we impose the optimality condition, we find that it is in the limit of the time step that goes to 0. This gives this equation, which is equivalent, the same equation of the original McLachlan's variational principle. So not the modified time-dependent variational principle, but the McLachlan's variational principle. And as you can see here, we have the real part of the quantum geometric tensor, not the imaginary. And the real part is symmetric. So it's more stable to invert. If we want to use the same method as before, it would be nicer to have this equation, not the one before, because it's simpler to invert. But we do not invert it, so we want to know how many evaluation of quantum circuit we have to do. So we have 2n circuits to evaluate the gradient. We have m, most optimization substeps, and a number of ns shots per circuit evaluation. So a total of circuit evaluation that is less than 2 amp per ns and the evaluation. So a number of evaluation that scales linearly with the number of parameters. If m does not depend on n, because if m is a linear function of n, so the number of optimization substeps scales with the number of parameters, we are back to n squared. So we have to check it, and we will see it later. So yeah, we have a lot of nice properties. So we wanted to use like a toy model to demonstrate this algorithm. So we applied this algorithm to the study of the transverse field Ising model. So which has the following Hamiltonian of we used a chain of 3 spins. We have an interaction on Z, and a transverse field along X, which acts locally on all the fields. And as ansatz, we considered the following, which is picked here, and is an hardware efficient ansatz, and can scale yeah, both in depth, if we want to repeat the structure d times, or in width, if we increase the number of spins, so qubits. And yeah, the first thing we measured is how much error does our time evolution accumulates. So basically, we measure this, that is the integrated infidelity, but more practically, this is how much error we are accumulating. We measure the overlap with the exact time evolved system using a classical quantum simulation algorithm, because basically this is an 8x8 matrix. Yeah, 3 spins. So it's very, very easy to do on a classical computer. We compared we calculated the overlap, and we integrated over all the time steps. And we did it both for our algorithm and for the previous time-dependent variational algorithm. And the results were, I think, pretty impressive, because as you can see, at fixed number of samples, we accumulate like an order of magnitude of less error than the previous algorithm. So here samples indicate everything. So the number of time steps, parameters, the number of optimization shots, and so on. So basically, every time a circuit is created on a quantum hardware and measured is calculated here. And yeah, if I have a fixed number of samples, so a fixed number of circuits, yeah, I am more stable on the PVQD with respect to the TDVA. And I have to add that these simulations are performed on a classical simulation of a quantum computer, but with the shots. So not on real hardware, not simulating the hardware noise. So this will be our next step, but this is a classic, perfect exact simulation, but with noise. So just because we are sampling with statistical fluctuation, the value, the TDVA accumulates really much more error than the PVQD, because as I was saying, this is due to the inverse of the matrix. And we used also this wave function that we created to evaluate some observables. And in this case, we measured the magnetization on the spin chain. And yeah, we can see that we used less shots on the PVQD to reproduce these observables curves. And both the methods tends to the exact solution as the number of shots goes to infinity, but we need less shots. And then in the end, we also we proved the efficiency. So we increased the number of parameters, and we evaluate how many samples we needed to complete the time evolution. And as you can see, the number of samples required by the TDVA is fixed. It does not show error bars, because yeah, it's not iterative, it's fixed. While the PVQD is iterative, so we did multiple runs, and we also fixed the step error, and we evaluate how many samples we needed. And yeah, as you can see, the asymptotic scaling is not quadratical, but it's still linear. So this means that the number of optimization does not depend on the number of parameters. And yeah, the more we increase the step error, the more optimization will be needed. And this means that we have these fluctuations when we increase the step error to 10 to the minus 5 from 10 to the minus 3. And yes, we also looked at a single time evolution. And in this case, you can see above the number of optimization steps per time step required, and also how the accuracy goes from above the threshold that we fixed to below just needing this amount of optimization steps. And as you can see, there are some time steps that does not require any optimization step. This is because we considered as an initial proposition for our shift at time n, at step n, the optimal parameter shift found at step n minus 1, so at the previous time step. And this is shown to be an optimal choice. So if you look at it in a single time step, we see that, yeah, basically using this optimal choice, we have that the first error, the error function, the loss function is more or less 10 to the minus 6, which is already below the threshold. So yes, this is optimal, so does not require any optimization, and we can proceed to the next step. So we basically restrict to one measure of the loss function without n and so on. So this is optimal, but this can be optimal in general. Maybe there are systems in which this is not optimal, but we can change. So this is the freedom given by the variational approach. And this basically ends what I have to say about the algorithm. So to recap, we have that the good points are that this is efficient. We know that the number of measurements scales linearly. We have it is more robust with respect to shot noise. We don't know about hardware noise. We have we don't need the evaluation of matrices, of ill-conditioned matrices, and we don't need ancilla qubits, and the system does not scale with the number of steps as a Trotter does. But there are some problems. The problems. The first problem is the problems common to every variational algorithm is the fact that we have a bias error introduced by the fact that we are using an ansatz, which is a problem which is really similar to machine learning. I don't know if some of you has done some machine learning courses. We have this bias error given to the fact that we are using a fixed neural network, a fixed ansatz to reproduce the state. So we don't know if this ansatz is good for every time t. And also that to measure the overlap, we have to double the depth of our circuit. So we are limited in the depth of the ansatz because we have to consider 2 times the ansatz plus a Trotter step. And yet we don't have a bound on the number of optimization steps. So yeah, we just checked it heuristically, as you have seen before, but we don't have an analytical bound. Maybe it can take like n to the 7 time to optimize, but we don't know. We just checked. It may depend on the system. It may depend on, or it may be analytical. This is future work, I think. And also, yeah, I did I was studying another thing, so I did a little comparison with Trotter. This is only to add something at the end. And as you can see here, I studied another system, which is the Heisenberg model, with on 3 spins on using the PVQD and the Trotter, and the PVQD with the following ansatz that you see here can be considered as a Trotter step of depth 3 because it has 2 times this structure plus a single Trotter step. And as you can see, it performs better than Trotter with n equals 5. So it's good for Heisenberg model. Yeah, but it was just a test of mine, not in the paper, not the main reason of the article. And yes, at the end, yeah, I put some outlooks. I also put the archive number if someone wants to read more in depth the article. And some outlooks are the following. Maybe some of you have other ideas, I don't know. But I thought about to try algorithm different systems. So study the time evolution of other systems, physical interesting systems, maybe some phenomenon, physically interesting phenomena. Use it to simulate adiabatic evolution, can be interesting to approach optimization problems. Try with noise model or on hardware, which is quite difficult, from previous experience on using hardware. And the freedom of these iterative methods is that we can use more sophisticated optimization procedures. So we used like standard gradient descent that is very, very simple, but we can use adaptive learning rate, ADAM, ADAGRAD. I already introduced ADAM as an optimizer for PVQD, which is a really good optimizer for neural networks. But it can be, with a closer introduction in Qiskit, we can use all the optimizer of Qiskit that are a lot and can be very, very useful. And to know if there are bounds on optimization, maybe use it to measure correlation functions, which are very, very interesting for the dynamics of quantum system, and maybe the possibility to vary the ansatz during the time evolution, so make the ansatz dynamic in order to decrease the bias error due to the ansatz choice. So these are my thoughts about what we could do to improve these methods. So this basically ends the presentation. So thank you. And I was said also to invite you, if you want to apply for a PhD, since also Arthur was saying to me that he's looking for a PhD, that the Computational Quantum Science Lab is hiring PhD students and postdoc. So yeah, come and check if you want.
Thank you very much, Stefano. I will put the cameras on for everyone. Here we go. So let's open the floor for questions from the assembly. I see that you are applauded from multiple actors. So yeah, it was a great presentation. Thank you so much. Please, if you have any questions, don't hesitate to just unmute yourself, or you can also ask in the chat if you cannot talk.
Yeah.
Hello. First, thanks for the presentation. What other problems did you try to solve with your techniques?
Do you mean what type of phenomena, what type of systems?
Or, yeah, mostly Ising models, or?
Yeah, yes, basically yes. I would like to use it also for molecular Hamiltonians. I don't know, because basically I started with quantum chemistry, quantum computing for quantum chemistry. So I really like that part, but yeah, I haven't done it yet. So I just want to think about maybe a problem which can be interesting to study the dynamic, and we'll try it.
Okay, and why did you try this kind of trial function?
Oh, yeah, I tried a lot of trial function, but this one is because it's pretty much okay. So let me if I can share again the screen. So I will show you. Okay, so here, okay, this is basically what a trotter steps looks like, but we have the freedom of choosing the gate that we want. So here I used Rx and Ry alternatively, and this gave good results, so I kept. But for more complicated system, like confined system with more fields, longitudinal and transverse field, you may need more complex ansatz, more complex circuits. Like I don't know. This one is very similar to a circuit that is used on quantum chemistry, which is hardware efficient, that alternates layer of Ry with layer of C-notes and something like this. but also in quantum chemistry, you may need very, very deep ansatz, like the unitary couple cluster ansatz, which is very, 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 very deep. And yeah, you are basically some sort of limited some way, but not so much, by the fact that we want to use the parameter shift rule. And the parameter shift rule cannot be used with every possible quantum gate that you want. Basically, every quantum gate that is an exponentiation of a Pauli string with an angle. So, and also fixed gates that are not parameterized, so you don't need the gradient on it. But yes, this is basically the.
Okay.
Maybe there are answers that are better.
Okay, great. Thank you very much. We have a question in the chat. Is it possible to have the slides of the presentation? So
yes, I think. Yeah.
Yeah. Okay. So we might
will,
upload
maybe,
them.
Yeah. I think that don't know. Maybe I can upload it in the Slack. I don't know.
Yes, I think in the Slack it would be great. So
because
for those
now they are in the Keynote format, but maybe I can do it a PDF that are.
Yeah, that might be great.
Later, I think.
Sure. So I will share in the Zoom chat right now the link to the Slack for those who can join us, and basically you can follow over there all the next events that are going to happen and projects that are going on with the association. Just before that, I wanted to. So is there another question before I ask mine? Okay, no. So yeah, I basically had a question myself regarding the class optimization procedure. So specifically for the number of parameters you optimize for the specific algorithm, would you say like it's all related to the ansatz? So regardless of the hardware that you want to implement the algorithm itself, or do you have a significant change based on the evolution that you want to simulate, or the parameters that you want to match for the parameter shift rule in this case? So does it change the choice of number of parameters, or is it uncorrelated?
Okay. No, it's uncorrelated, I think. Yeah, you have an ansatz and you can measure the gradient on it using the parameter shift rule, and basically you are limited by the choice of the gates, as I was saying before, the exponential of these Pauli strings. But yeah, you are not limited in it. Also, if you want, you can choose whatever you want as a gate, but you can't use the parameter shift rule, so you are reduced to use like finite differences, which is approximated, and you may have slightly worse results, I think, because it's not the good of parameter shift rule is that you have to evaluate the circuit that's with shifted parameters, as the name says, but you have the exact estimation of in principle, you have the exact estimation of the derivative. So if you start with bias 0, it's better than starting with some bias on the derivatives, because you have to add the noise and so on. So it's better in principle. And also in the beginning, I was thinking about if you're referring to hardware in the sense of superconducting ion qubit, but yeah, it's not limited. It's our hardware agnostic algorithm.
Yeah.
So there are in different hardware, there are gates that are preferable. Like, for ion traps, you have multi-qubit gates that are very, very easy to implement, while on superconducting it's different.
And what about the role of the time step that you use to build the optimization? So did you notice like high dependency on the width of the time step that you choose between 2 rounds, or how was it chosen to match the?
Okay, so that's a pretty good question, because of course, if you think about having a long time step, it's not a good idea, because for 2 reasons. For the first reason is that since you are approximating the time evolution with a single time step, if you use a time step which is too big, you're doing the trotter error, basically. So you are back in the same error of trotter. So yeah, you have to choose, in principle, a time step which is little enough to be trotter exact, something like this, which is.
But did you notice some change on the optimization process? So because you said you explained that you chose the previous weight based on the best optimization round on the previous time step, right?
Yes.
So when you increase the time step, I figure that you get further away from this optimal optimal step.
Yeah. Yes, it's exactly like this, because this is since you are like evolving time step per time step, the second time step is very similar to the first one, since the system is continuous, derivable, and so on. These are all these nice properties. So this is an optimal choice like this, because you expect that the system will evolve slightly different from previous one. So it's this is why, it's exactly as you say. And also you don't have to choose it too little, because too short, because if you are evolving too short, the overlap is already big. So that's the reason why we put the loss function, which is time step independent, because otherwise I just choose a very small time step, and it does not optimize and goes like random. This is the reason.
And so they would, this would amount to like a diabetic optimization in a case where you would increase, you would reduce the time step, so you would like move away from the adiabatic path in your optimization process. But in this case, so you were saying about the scaling of the optimization round, so it reduces significantly based on the fact that you are able to produce a good time step, right? So if you put it too big, it's you have further optimization rounds, and if it's too small, you might also have this this limitation. So overall, would you say that the number of rounds, like, and maybe also for this is another question, but this has to do with the total sampling of what you do with the computer for measuring the expectation values of the Pauli observables, for example, in the Hamiltonian you showed before. So in total, how much time do you take to simulate a system like this on current hardware? Like the simulation overall could take could be quantified in that matter?
Yeah, do you mean computational time, so real time?
Yes, yeah.
Yeah, at the beginning, it also depends on how you code it, because Qiskit is very sensible to reinitializing every time the circuits. So in the principle, like for 60 time steps for the system that you have seen, it was like 20 minutes, 30 minutes, like presentation on a common laptop. So now it's faster because I rewrote it, optimized it, and now I'm also working to further optimizing it. It should be even faster, and we are incorporating it in the Qiskit framework, not in Qiskit because we have to wait, but in the Qiskit framework, so it should be faster. I don't know, but it should be.
Great.
Otherwise, it's work for nothing. But it
sure, of course.
Faster.
So, any chance that you will upload the example on the Qiskit library, like a use case for the algorithm? Or
yeah, I hope so. Because in also in the computational quantum science lab collaborates also with some collaboration with IBM. So maybe we can improve. We can implement it in Qiskit. But at the moment, if you are interested, I published the code on GitHub. So let me just take the link. A second, and I can copy it in the chat if you want to play around with the code. This is basically the version that I used for the paper. So it's not the new one, but the new one had some problems. So when it's basically fixed, but you have to find the time to put it on GitHub.
For sure.
Yeah.
Amazing. Yeah, so it's really great to have such open source material as well, for especially those papers. So it's always cool to have the chance to dive inside the code and see for all the future quantum software engineers in the assembly.
Yeah, I'd also suggest to go to not because I think that most can do better. But yeah, that's the idea.
Yeah, but it's a starting ground as well. And so in the frame of starting in the physics, so you can tune up the model as well. And I figure that, as you said, there are a lot of ways to improve the code. Or
the main power, I think that the main reason to prefer it is that it's iterative. So we have a lot of way to improve because basically all neural networks style optimization is iterative. And we have a lot of ways to improve. Maybe, just like when I'm using Adam for bigger systems, like 11 qubits, not so big, but bigger.
Yeah.
Adams is a great help because it adaptive modify the learning rates of every parameter. So there are parameters that are more important, and the ansatz of quantum circuits are strongly nonlinear. So it's difficult to know which is the parameter that works better, which is more important. And so Adam is a great help for this. But yes, there are maybe other optimizers that are better.
Definitely. All right, thank you very much, Stefano. I will launch a final check if there are any questions remaining. If not, I think we'll close the session for tonight. Okay, so it doesn't seem, so I will stop the recording right now.